Welcome back, everybody. This installment of the engine build series is going to be about the prediction and planning for the performance of the motor, targeting a specific horsepower based upon the engine that I'm building and how I want to use it, the application that it's going to go in. And we have to look at the factors that are going to come into play in determining how much of that horsepower I can achieve. There's about four different ones, four major categories: displacement, your cylinder heads, compression ratio, and camshaft. All those things come together, and it's actually a very predictable formula, not voodoo. There's math behind all of this, and you can very accurately predict the amount of power a motor is going to make if you know the performance of the individual components that you're going to be putting in it. So that's what we're going to do right now. The block's going to be back in my hands hopefully by the end of this coming week, and it will be time to start putting it together. So there's not much time left to do this planning. Let's go over all the major categories. We'll highlight them. There's about four that you have to take in consideration: your displacement, your compression ratio, your cylinder heads, and your camshaft. If you match all those things together, if you build a motor that plays nicely internally, you're going to get really good horsepower out of it. So without further ado, we're just going to start tackling those topics one by one, and we'll see what those numbers add up to at the end. Okay, so here we have the information needed to calculate the displacement of a motor. You need to know the bore, you need to know the stroke, obviously you need to know the number of cylinders. And the formula for determining the displacement is pi r squared times the stroke times the number of cylinders. Pi is 3.14 infinity and non-repeating. I've always used 3.1415 for the most specifics. So that's what I'm using right here. The radius is half diameter. Now you notice my bore is 4030. Well, the radius is half of that, so the radius is 2.015 inches. And then you square that, and then you multiply that by the stroke, which is 3.48 inches. So the next line down, you end up with pi times the square of 2015, which is 40,062, times the stroke. That gives you 12.755 times 3.48 for the stroke, and that gives you the displacement of each cylinder. Each cylinder is displacing 44.39 cubic inches. Now we have 8 cylinders, so you multiply that by 8, and that gives you your displacement, 355.10 inches. That makes this a 355 Chevy. Pretty simple math, and the formulas are available online. Probably should have learned this in 8th grade geometry, and I probably did, but that was like 40 some years ago, so I had to look it up again. That's our displacement. So that's the first thing we need to know in calculating the engine's performance, is how much volume do we have to work with to produce power. Pretty straightforward. Those are the numbers right there. Let's go on to the next category, which is going to be the compression ratio. Okay, let's talk about compression ratio now. The first compression ratio is the static compression ratio, and that is the one you'll almost always hear people referring to. That is the compression ratio with a completely closed cylinder using all of the stroke available to compress the maximum volume of air into the minimum amount of space to give you that ratio of X to X, or X to Y. The information you'll need to calculate this is the bore, the stroke, the head gasket bore, and that's a little different. The head gasket's ring around each cylinder actually adds a little bit of volume because it doesn't match up right to the dimension of your piston bore, which 4030, 4060, it's a little bigger. And that fire ring has a little space around the opening of the top of the cylinder. Well, that has to be taken into consideration because that adds volume. So while I have a bore of 4030, I'm just going with the fact that the head gasket will be a little bit bigger on its fire ring. So I'm going to go with a 4060 head gasket bore. Then you've got the compressed thickness of the head gasket. This is where you get to play around a little bit, and it is the thing besides like the CC volume and the pistons that allows you to fine tune your compression ratio. I'm going probably with a 30 thousandths head gasket compressed thickness. So that's what I listed right there. But you can adjust that up and down. If you want to lower your compression ratio, you go to like a 40 or 45 thousandths. If you want to raise your compression ratio, you get to use a thinner one. You can go down like to a 28, 29, even down to a 20 thousandths compressed gasket thickness. Wouldn't go too thin on a street motor. Heat warping and everything affects all that. So you want something to hold the head together. So you want some volume or thickness there for a head gasket. 30 seems reasonable. It's a little bit on the lower end, but it's reasonable. Then you've got your combustion chamber volume. That refers to the cylinder head. That's the cutout in the cylinder head that holds the valves, and that dome has a volume, and it's measured in cubic centimeters. The two standards on Chevys are like 64 cc for the small chamber and like 72 cc for the large chamber. So wanting to go with a higher compression motor, I'm going to use the 64 cc cylinder heads. Then you've got the piston volume. That piston volume is going to be 0 if it is a true flat top with no valve reliefs. It is going to be a minus if it's a dished piston, and not even specifically a dish piston, but a piston with valve reliefs in it has a minus cc volume. That is adding to the volume because there's no material there. It's a hole in the top of the piston. That hole has to be filled with air, so it raises the amount of volume in the cylinder. So you have to add that in as a additional volume in your combustion chamber. Then, as you see, if you have a domed piston, that would be a plus. That's actually going to take volume away from the cylinder. So even at a given stroke at the top of the travel of the piston, when it reaches TDC, a domed piston is going to give you a much higher compression ratio because that dish or that dome space is taking up space that air could have taken up. So that raises the ratio. Then you have your deck height. Now that is not the quench. The quench is the amount of space between the head gasket, the deck, and the top of the cylinder. So that isn't taken in consideration in your deck height. The quench is factored in with the head gasket thickness. Then you run those through a calculator. The formula for this is pretty involved and it's not worth going over because there's dozens of compression ratio calculators available on the internet. I use one from Summit Racing on their website. These numbers all plugged in give me a static compression ratio of 9.87 to 1, which is kind of right where I wanted to be. I wanted somewhere between 9.5 and 10 since I'm not going to boost the motor and it's only a 2-bolt. I didn't want to go over 10 because then you got to start worrying about things like knock detonation. You got to run higher octane fuel. And this motor really, I don't want it making more than like 450 horsepower. I don't think I'm going to get close to that, but that's about as most as I'd want to put into a 2-bolt main Chevy. And the internal rotating assembly components are rated only to 500 horsepower. So I want to keep it safe. So we're going to give it some space to have a little, let's just say, compensation for power. So we're going to go ahead now and use these numbers, and we're going to calculate the dynamic compression ratio, which is important because that's the one that really determines how much power you're going to make. Okay, now let's talk about the dynamic compression ratio. The variables involved in calculating the dynamic compression ratio beyond what we're required to calculate the static compression ratio are your rod length and your IVC, intake valve closing point. This goes under the assumption that your intake valve is still going to be open for a period of time, a duration, while the piston is starting its travel up on the compression stroke. So we know the standard Chevy connecting rod for a small block is 5.7 inches, and those are the rods I have. The IVC, I don't know exactly what it's going to be because I have not selected the cam yet, but the ones that I've looked at, it seems to be an average of about 41 degrees of duration for the IVC point. So for 41 degrees as the cam is rotating, the intake valve is still open as the piston is coming up. Now you calculate all that together, and again, you do it with a calculator online because the math is involved. The effective stroke is only 3.14 inches. You know that the static stroke was 3.48 inches. So I'm losing 0.3 of an inch of stroke because the valve is not closed yet when the compression stroke is beginning its cycle. So my effective stroke is less than my static stroke. That's why your dynamic compression ratio is almost always lower, should be lower than your static compression ratio. Then there's some other factors that you can put in to fine-tune your dynamic compression ratio, like your density altitude. Where I live, somewhere between 600 and 1,000 feet above sea level on a standard day at 2995 inches of mercury, gives me a dynamic compression ratio of 9.08 to 1. And if I corrected it for altitude at 1,000 feet, it's 8.88 to 1. Hotter days, that altitude corrected dynamic compression ratio is going to be even lower. That's why that's why we all know that engines make less power on hot days or at high altitude because there is less air. There are fewer air molecules per volume to use for combustion. So that is the dynamic compression ratio as calculated with the components that I'm going to be using. So I know that my static is 987 to 1, and I'm going to go with a dynamic compression ratio of 9.08 to 1. So now we'll go to the next factor in the horsepower projection, which is the cylinder head performance. Well, let's talk about cylinder heads now. The single most important part of producing power in an engine is the cylinder head. That's not to say the others aren't important, but these make the biggest difference. Cylinder heads allow air in and allow air out, and that is the key to an air pump. How much can you get in? How much can you get out? Well, that all comes down to volume and efficiencies in your cylinder heads. Now, the cylinder heads that I have been looking at, and the ones from a price point and performance that make the most sense for what I'm trying to do, seem to be the Pro Max 200 small block Chevy cylinder heads. Not going to go into the specifics on the price, but they're mid-ranged heads for a set. They have an intake valve of 2.02 and an exhaust valve of 1.60, and they have an intake runner CC of 200, which is a little bit over average. Average would be about 190, 185, 190. I think the stock Chevys, the Vortec heads were like 185 cc intake runners, and then you can get like 220, 230 on a high end. The 200 makes sense for the engine that I'm putting together. Now with cylinder heads, efficiency is what you're looking for. And the efficiency is measured in several different points of lift of your intake valves, and it is measured on a flow bench. Flow benches literally do that. They put the head on a bench and they see how many cubic feet per minute of air flow through the cylinder head at a given pressure. It's like 28 inches of water or 28 inches of vacuum, if you want to call it that. That's the standard measurement point for a flow bench. Now these do, thankfully, and it's like one of the very few sets of heads that I was able to find on the manufacturer's website that actually gave you flow bench numbers. So good on them for doing that. And I found 3 different points of lift that I could check the flow numbers on. Sorry, I was stabilizing the camera a little bit there. And at 400 inches of intake, that'd be 0.4 inches, they flow 242 CFM of air on the intake side, and they exhausted 179 cubic feet.
that is not balanced, and that gives you your efficiency percentage. If you divide the 179 by the 242, you see that 74% of the intake air is, or exhaust air is being let out versus the intake air. Then at 500ths lift, or half an inch lift, the efficiency drops to 73%. At 600 inches of lift, the efficiency drops to 72%. And those numbers just keep falling because the efficiencies get lower as the intake and exhaust valves reach max extension. The reasoning, I suppose, is because the hole is only going to get so big on the intake and the exhaust port. So you can only let so much air in, so much air out, no matter what you do. Now, 75% is considered good, I think, from what I've been reading. When I say good, I mean acceptable. Target efficiency that I would like to see is about 80% in the lift range of the cam that I'm going to be selecting. So knowing that these flow only 74 and 73% respectively between 4 and 500ths of an inch of lift, which is where the cam I'm probably going to be selecting is going to live, there's ways to get that target back up closer to that 80 or better percent efficiency. The cheapest way, but the hardest way, is to port your heads. Go ahead and port the exhaust ports. Make them a little bigger, make them smoother, let the air get out a little bit quicker. That's going to increase the efficiencies. And then what you can do mechanically to increase the head efficiency is select a camshaft that has a dual profile. You'll look at cams and they'll have advertised lifts, and a lot of them are balanced. They'll be like 450, 450, 480, 480, 500, 500. Intake and exhaust are both the same. Those are single profile cams. Dual profile cams will have larger exhaust lift and duration than the intake. And that is to help compensate for the disparity in the efficiency of the cylinder head, to help get the exhaust gas out faster. I just said a word that made no sense. So selecting a camshaft can help offset the efficiency of your cylinder heads and improve them. But knowing these numbers is very important. When you select cylinder heads, do not get them unless you know what they flow, how they flow on a flow bench. And you may have to do a lot of digging, like I did. But you can find it, or ask your machine shop. They may have experience with doing flow benching for other customers, and they may have data sets on file for specific types of cylinder heads. The very common ones like Flowmasters, Darts, Trick Flow, AFR, airflow research heads are very, very good heads, and expensive though. So, but those numbers are out there. These are the ones I found for these ProMax heads, and these are probably the cylinder heads that I'm going to be using. So now that we know these numbers, we'll go ahead and look at the camshaft that I'm kind of zeroing in on using. Camshafts. So probably the second most important part of the horsepower equation is the camshaft, because it's telling the head when to open, when to close, and how much to open and how much to close. So camshaft, I'm still going around and around and around on which one to select, but keeping in mind this is somewhat budget conscious, I found the Lunati Barebone cam that has a good profile on it. It is a dual profile camshaft, meaning that the intake and the exhaust lobes are unbalanced, cheated towards the exhaust. It has an intake lift at 443 thousandths, an exhaust lift of 465 thousandths. That's with a 1.5 ratio rocker arm. I could improve that by going with a 1.6 to 1 ratio rocker arm and get the intake lift up to 472 and the exhaust lift up to 496. Those numbers are important because the ProMax heads that I was looking at had a maximum lift with the installed valve springs on them of 550. And I don't want to bump right up against the maximum lift. So that leaves me some overhead so I won't end up in a coil bind, and I won't end up in some seat pressure issues where I'm going to be putting a lot of stress on the valve springs that come with those Pro Max heads. Now I could always upgrade the springs. That's always a possibility, but on this motor it just doesn't make sense because it's not going to be super high performance. I'm just trying to get the most power reliably, safely out of a 2-bolt main Chevy. Now the duration, the gross duration, intake is 280 degrees on the intake and 290 degrees on the exhaust. But what we all use is the duration at 50 thousandths lift, and that is 214 degrees on the intake and 224 degrees on the exhaust. So that is a pretty balanced camshaft, and it fits within the range where I wouldn't have to necessarily go with a high stall speed converter if I do an automatic in the car that I put it in. You start getting up over in those 230 ranges on the at 50 lifts, or durations I should say. The cam profile shifts up the RPM range when you start doing that, and they don't make power and they don't like idling, so you got to run a high stall speed converter. So with this one I could probably get away with the factory or just a slightly improved stall converter, somewhere around maybe 1700 to 2000 RPM stall converter, and have decent idle performance and decent street performance out of it. The RPM range on this is advertised between 1500 and 5500 RPM, which is perfect for a street motor. I don't think this motor is ever going to turn more than like 5300 RPM anyway with a 2-bolt. So this cam makes sense. So we're going to go ahead and go with these numbers. And then I'll check the valve spring capabilities and all that with running 1.6 rockers to get a little more performance out of this cam. It's a cheap cam, runs like $120. It is a hydraulic flat tappet. I'm not going roller on this motor because that's going to be like $500 to $1,000 to do a conversion from a Gen 1 Chevy small block, which was designed with hydraulic flat tappets, to go to a full roller setup. I am going to do roller rockers, but it's going to be solid hydraulic lifters, just keeping it like in the factory design specs. So that's our camshaft. So we've gone over all of the factors, so to speak, that go into this horsepower projection. Now we can start plugging it all together and see just what I can expect to get out of this motor horsepower wise with the components that I've shown you. And this is the target. This is the goal. So it's money time. Going to go ahead and get the board ready and plug the numbers in, and we'll see just how much horsepower I can expect to make out of this motor. Here it is. Horsepower calculator. And I'm going to list all these calculators that I used in the description below. Links to the websites. Amazing stuff. I'm kind of engineer mindset. I'm not an engineer. I'm actually in IT, but I have a math mindset, and I love to know how things work, and I really get into the math and science behind things. So these calculators are really intriguing. In the video on my drag racing on my G37, the calculators were spot on. I was within 300ths on my quarter-mile time based upon the horsepower I knew I had from my dyno pulls on my uprev tune. I got really deep into the specifics of my car weight, the density altitude, being precise as possible. And it was almost no point in going to the drag strip. You know, I was like, okay, I know what my car is going to run now. And the calculator I used said at that particular day on that temperatures with the weights and powers, I should have ran a 13.8. I ran a 13.78. So can't argue with that. Now, the horsepower numbers, the calculator I used needed this information. The intake that I'm probably going to use is something, it's not necessarily going to be an Edelbrock, but it's going to be a dual plane, semi-high rise, maybe a carb spacer. And the carburetor is going to need somewhere between 700 750 CFM. The camshaft, as we just discussed on that Lunati, has an intake lift of 214 degrees, and it's a hydraulic flat tappet. The dynamic compression ratio we calculated as 9.08 to 1. And on the flow bench numbers with those ProMax 200 SBC heads, I extrapolated a little bit because my lift is going to be in the 460, 470 range, and I took the difference between the flow bench numbers of 400 and 500 lift, and I'm going to go with 250 CFM on the flow. Ran it through the calculator, and drum roll please, the engine, as I've spec'd it, should make 411 horsepower at 5589 RPM. RPM range, it's high, but I figure, you know, small block Chevys usually don't run higher than 6. They're happy, but probably between 3,500 and 5,000. So in that range, on the street range, I should be making somewhere between like 330 to 370 horsepower in most driving conditions. And if I want it on tap, I could have upwards of 411. Now those numbers will change based upon the any extra work that I do to the heads, like porting, polishing, and other hot rodding tips, you know, you can do, and may play with them a little bit. But this is exactly what I was thinking. A couple of videos ago, I said I think my engine's going to be between like 390 and 410 horsepower, and here it is. I mean, it's up on the 411, but honestly, when I dyno it, being my first engine, if it dynos out at anything over 380 horsepower, I'll be happy. The car it's going to go in, don't know. Like to find like a second gen Camaro, 76 to 80 Camaro, a little rough around the edges that I can just kind of work on after the engine stuff's done, do body work, get it as a nice little hot rod driver. Me and the missus can cruise around in our old age and just enjoy life a little bit. So thanks for tuning in again. I'm putting out a lot of videos. I just want to make sure everything's covered and you guys know exactly what I'm doing and the reasons behind it. It's important to me, for myself, to know what I'm doing, and if I can expel that information out onto the internet for anybody else, then I'm happy to do it. I'm also going to put some links down to some of the other people, these master engine builders that I've been watching, and their build series is Pete's Garage, I've mentioned before, Vintage Iron, Eric the Car Guy, Nick's Garage, big fan of Nick's Garage, big fan of Pete's Garage. Those guys are just awesome. They're just really good people, and they know what they're doing. I've learned so much from them. So there you go. That's how much horsepower I'm hoping maximum to get out of this. Getting the shop / garage ready for the engine build. Got me a new workbench set up, good workspace, very important to be organized, and that's the thing that I'm going to hopefully learn more from than the engine building, is just how to stay organized and work clean, work efficient, work smart, work at a good pace. So I got a nice little workbench set up, got the vise and got my tools organized, realized how many sockets I've lost over the years when I started putting them on new rails. So, wow, can't believe it, but we're getting there, man. By the 30th, hopefully the engine's done. I'll have it back here. We'll just start doing some videos, getting it prepped, cleaned, painted, and start putting it together. Please like and subscribe, share this with your friends, and I look forward to the end result at the end of this. We'll all see together. It'll be a surprise for all of us. So take care, be safe, much appreciation for watching, and I will see you in the next video.